Hello, my name is Sam Gradin. This is the demonstration video for the University of North Dakota's Department of Electrical Engineering Thevenin and Norton equivalent circuits adapted for use with the National Instruments MIDAC. Now a little background on this lab. We're trying to calculate Norton and Thevenin equivalents. These are useful because as an electrical engineer you might want to know what's happening just at two specific terminals of a circuit, as you can see here, instead of just what is happening in the rest of the circuit. So what we're going to do, instead of using traditional testing equipment, is use this National Instruments MIDAC. For setup, you're going to want to hook up the USB cord to your laptop or computer, hook up the proto board, and then collect your resistors for the laboratory. Now in the lab, it lists that you need two 5Ks, a 1K, and a 1.4K ohm to complete the lab. Now if you don't have all these resistance values available to you, you can use resistors put in series, like I've done here. You'll see that later in the circuit, just to find the values that are listed in the laboratory. Also, you're going to need 10 resistors to use as load testing values, so make sure to get those, and then you're pretty much ready to go. Just open up your Labview on your laptop and also launch the instrument launcher Elvis for the DAC and click on DMM, and then you're set to go. Now, to measure the resistance values before you put your resistors into the circuit, what you're going to want to do is connect the probes to the DAC. And I have my probes connected over to alligator clips over this resistor here. Open up the Elvis function, a multimeter function of the DAC. Click on ohms. I would set the mode to auto in this case and then hit run, and it's going to take a second to actually start functioning. Then you're going to get a reading, and this is my load resistor, so 5.63k ohms for a 5.6k resistor is appropriate. When it comes to the step of measuring voltages in your DAC, first thing you're going to want to do is actually put your circuit together and get ready to measure the voltages. It says in your lab that you need to use Ohm's law in Labview to calculate the currents, so that's easily done. But there's one thing to note here, is that because there's constraints on the DAC itself, you cannot supply a whole 5 volts to the circuit and measure correct voltage values. And why this is, I'm not really sure. But the easy way around it is you can actually click to supply 5 volts here, and then move over here, and what I've done is divide that voltage by 10 so that you're actually supplying half a volt to the circuit. And then you can actually correct your readings as well by multiplying the red voltage by 10. So you're completing the circuit as shown in the diagram of the lab, however you're going about it in a different way. And once you do that, you take your voltage, you read it, voltage divided by resistance is current, and then maybe calculating current in milliamps would also be a good thing, because some of the currents in this lab can be quite small. So once you have that complete, you can measure each one of your voltages in your circuit. One thing to note though is make sure that you put your resistance value in here. Right now I'm going to measure the voltage across the load resistor, which we measured to have a resistance of 5,630 ohms earlier. So then I can just start this circuit here. And I have a wait timer on this, so I'm not getting data coming in constantly, but every second this will refresh. And as you can see, I have a voltage of about 1.5, a little less than volts, and also current going through that resistor. So complete that for the circuit and then move on to I short circuit, R Thevenin, and V Thevenin. When measuring V Thevenin, what you're going to want to do is actually remove the load resistor from the circuit itself. So you measure just the voltage across terminals A and B. So once the load resistor is removed and you've placed your analog inputs at the correct locations, you can run this, and then you get about 2.5 volts for your V Thevenin. Now measuring I short circuit, you want to leave the low resistor out of the circuit, but this time instead of using the Labview VI that we have been using, I'm going to use Elvis for this. And go over to amps, make sure that your probes are in the correct location, and hook them up across terminals A and B so that there's a break in the circuit, and then you can hit run. Also make sure that you do run your power supply, and you end up with about 0.06 milliamps DC current. Now to measure R Thevenin, all you have to do is short the power supply. Make sure that your positive is connected to your ground, and completely removing the VS out of the circuit. And then you can leave your alligator clips kind of where they're at to measure R Thevenin, and you start your ohm meter here. We get about 3.89, 3.88 k ohms, which is what is expected. Now for the last part of the lab, we're going to verify experimentally that when R Thevenin equals the load resistor value, that you have maximum power transfer to the load resistor. So in this VI, you're going to have a couple things that are going to be different. First, you're going to do the same thing to voltage as you did in your last VI, dividing it by 10 so that your 5 volts actually becomes half a volt because of the constraints on the DAC. They're going to multiply the voltage read by 10 to get back to what the voltage should be. Then you want to take voltage squared divided by resistance, which equals power, and then it might be useful to find milliwatts in this case as well, because a lot of the powers measured here are quite small. So what the lab instructs us to do is have these 10 different values of load resistors here, all the way from 1 ohm to 5.6 k ohms. I would recommend including 3.9 k ohms, which is the value of our R Thevenin, somewhere in that sample of resistors, and you connect them across where terminals A and B would be, so the same place our last load resistor was at, and just measure the voltage across those terminals. So we can run this VI. We have our inputted resistance of 4,630, gives us a voltage of about 1.35 and a power of about 0.40 milliwatts. So thank you for watching this demonstration. You should know everything that you really do need to know to finish your laboratory, make sure you do your pre-lab on Norton and Thevenin circuits, and also include in your lab report why you think that the DAC is either appropriate or inappropriate for this lab, and how do you believe it was utilized, and whether it was utilized well or poorly. So thank you again, and goodbye.